Okay. So last time we learned about what is machine learning, and we have learned in machine learning algorithms there are several categories. So first, supervised learning and unsupervised learning. The biggest difference between these two is in supervised learning we have to use the ground truth, right? But in unsupervised learning we don't have to use the ground truth. That's the big difference. And also clustering, we have learned about clustering, classification, and regression, okay? So clustering, this is an unsupervised task. We only use the input uh, and we somehow categorize, reveal their categories using their distribution, okay? So, and also we also learned about k-means clustering algorithm. And this classification and regression, those are supervised learning algorithm, but their difference is in the classification, their output is discrete, but regression, their output is continuous, okay? And also, we will also further learn about this detection and segmentation, but these are also the supervised learning, okay? And also, we briefly learned about the BOW representation, which is the bag of words representation, and that was the state-of-the-art algorithm in the year of early 2010s. Okay, so spanning 2 or 3 lectures, we will learn about this BOW pipeline. Okay, and basically, that's the a way to construct this type of histograms from the images. So after making these histograms from the images, we will classify this histogram. That is the pipeline for the image classification. So, but I mean, in the text, I have to say the words are predefined, okay? But in the image domain, it is not defined clearly. So we have to make that by extracting all the features from the images, and then by applying the k-means clustering algorithm on that, we can take the centroid, and that centroid becomes the visual words, okay? And then using that visual words, we can construct this type of histogram for each image. Okay, are you guys following this? Okay. And then we will apply the machine learning algorithms to discriminate these histograms. So and today we will learn about this, okay? And this is how we extract, uh, I mean, features from the image. And there was already some popularly used feature descriptor that can somehow detect some useful patches from the image and then describe those patches as some vector. So we will just use that, okay? There are plenty of feature extractor using this type of concept. So I mean, in the implementation, we will use those, I mean, predefined feature extractors. So you can just believe them to work. And then after extracting all the features from all the training images, we can apply the k-means clustering algorithm to categorize those features and take the centroid, then this becomes the visual words, okay? And we also learned about this k-means clustering algorithm. And then when new images comes, and by extracting the same local features, we can map each features into one of the visual world, their centroid, okay? By doing that, we can construct the histogram for the new images, okay? Okay, this is the BOW pipeline. And today, I'm gonna, teach you about this support vector machine. Okay, so this is one of the, popularly used machine learning algorithm right before the deep learning. Okay, that was the state-of-the-art algorithm in 2010s. Okay. Um, okay. So, I mean, given this type of samples, so there are two types of samples, which is from red and which is from white. Okay, there are two classes. Okay, and we have to build some mathematical model that can classify these samples into two classes. Okay, and there are actually many boundaries between these two groups of samples, right? But which one is the best? I mean, there could be a lot of criteria to decide which one is best. Okay, but in SVM, we will find the one straight line that can maximize the margin. So here, the margin is defined as the distance between these two dot straight line. Okay. And I will further explain what is this dotted straight line and what is the real, I mean, straight line. Okay. Um, we have to first define I mean, normally we have if we have two-dimensional input, we will call that to have X and Y values, right? But we will call that as X1 and X2, okay? So, I mean, this sample is having this amount of X1 value and this amount of X2 values, right? So given this two-dimensional feature, I mean, two-dimensional values, we can position each sample into this two-dimensional graph, okay? So X vector is meaning each sample's coordinate, okay? And we also have to rebuild this W, which is the parameter for this SVM, the machine. Okay. I mean, this is similar to the function f I already told you. Okay. So we have to decide function f, actually the machine. We have to update their parameters to output something we are desire. Okay. I mean, this SVM is, you can interpret this as some function, okay? And if we input our input X vector into this SVM, it will output something. And that is kind of in SVM, that's the class information, okay? And to initially, and before that, I have to explain this. So, I mean, SVM, their how to say formula looks like this. So we first, given this X input, which is the sample, we will multiply our parameter W, which is actually the vector. So W1 is multiplied to X1 and W2 is multiplied to X2. And also we will add one scalar value to output something, okay? This is our, how to say, the function f. Okay, wx plus b is the function f of ours. But the thing is, we have to update these w and b parameters to output 0 for these locations. Okay, so I mean, this location is the line that can completely divide red samples and also the white samples. I agree with that, right? So, I mean, this W and B has to be updated um, to output 0 for these samples, okay? Okay. I mean, if it is like that, then if some sample is located in this part, okay, in this part, then if some samples X is located here, then their WX plus B becomes positive. And if some sample X is located in the beneath of this straight line, this WX plus B, which is function's output, becomes negative. Okay. So, I mean, using this type of sign of the function's output, we can classify samples, each sample, right? So for achieving that, I mean, this W and B should be updated uh, to make to make the samples lie on this straight line becomes 0, right? Okay, so I mean, this is kind of the function f we will learn. Okay, uh, for given ith sample x, we will multiply our parameter w and b and take their sign and use it as the class information. Okay, this is our function f. Okay. But the thing is, support vector machine, I mean, still, there could be a lot of functions. I mean, there could be a lot of functions, a lot of straight line that can divide these red and white groups, okay? But the thing is, in SVM, before making this straight, instead of directly making this straight line goes to, output 0 value, they, uh, how to say, draw another two straight lines, okay? So that is actually this. So this dotted line, those are the two lines whose W x plus b is equal to 1, or their values are equal to -1. So, I mean, this one is lie on the positive side of this Wx plus b, right? So this line is actually the line that output 1 for this Wx plus b, okay? It is slightly above the Wx plus b is equal to 0 straight line, okay? And this dotted line beneath the this straight line is the one having this equation, right? And then they calculate, so this is two lines slightly beneath and slightly above the, how to say, this straight line, Wx plus b is equal to 0, okay? And then they define margins, okay? They define the margins. Um, I mean, they define this Wx plus b is equal to either +1 or -1 to be the straight line that explains the samples which is close to each other. Okay, so I mean, those samples you are seeing pointed by these green arrows is the samples which are close each other, closest to each other, right? So this sample is close to the white samples, right? Are you following this? Okay. And these two samples are close to this closest samples, which is closest to these red samples, right? Okay. And we will make these two lines for this boundary samples. Okay. So I mean, in this SVM, they will update W and B to make the boundary samples meet this condition. Okay. Are you guys following this? Okay. And also, why this support vector machine is called as support vector machine is, I mean, machine is denoting some function, right? And support vector means the vectors that support the boundary, okay? Somehow you can think like that. So support vectors are the samples lying on the boundary, lying close to the boundary, right? That's the support vectors, okay? So, I mean, this is different from other similar algorithms that can classify or find this straight line that can divide the two categories. So that's why actually this support vector machine is called support vector machine, because they are first capturing the boundary samples as the support vectors, and also they calculate the margins. They define margin as the distance between these two straight lines. Okay, so how to say, this Wx plus b is equal to 1, and Wx plus b is equal to -1. That is two straight lines. And we calculate the distance between these two straight lines and define it as the margin. And in support vector machine, we try to maximize those margins. Okay. So I mean, we can draw a lot of straight line when dividing this type of two sample distribution, right? But indeed, we first capture the one closest to the boundary and define this as +1 and this as -1, and define this as margin and find the one that can maximize this margin. And if you, I mean, also in some, for different maybe boundary, you can also get these two as kind of these support vectors, okay? And calculate this margin, and you will decide this as the final maybe straight line that can divide these two distributions. But you will choose the one your margins are maximized. Okay, that's the support vector machine. Okay, are you guys following this? Okay, this is because we are given, I mean, when deciding this SVM model, we are given a limited number of training data, right? Sometimes this training data is not fully explained about this boundary, right? Okay. So, I mean, this is not bad situation, but if you're, how to say, training data is very sparse like this, okay? Like this. So using this few samples, your boundaries can be not to say optimal. Okay, but I mean, so I mean, when you directly find this straight line that can roughly divide these two distributions, that cannot be non-optimal. But if you find this type of support vectors, okay, and by finding the straight line that can maximize these margins using fewer training samples, it can be how to say, more optimal. Okay. So that's why this support vector machine is working better than others and was one of the state-of-the-art algorithm. Okay. in right before the deep learning. Are you guys following this? Okay. Okay. And the margins could be fine. I mean, I think you already learned about uh, so I mean, this is the boundary we have to calculate. I mean, we actually will calculate the margins now, okay? But I believe you already learned about the formula that can calculate the distance between straight line and a point, okay? So, I mean, if this is the straight line, and if some point is lying on this straight line, I mean, this is the Wx plus b is equal to 1, okay? And let's assume that one point, x0 and y1, is lying on this straight line, and we want to find the distance between this xo, comma, yo, and this straight line whose equation is wx plus b equal to 0, right? Then their formula is actually like this, okay? And as far as I remember, that looks like this, right? Because this is lying on this line, this is becomes 1, and this is simply the norm of the W, right? Are you guys following this? So because of that, the margin becomes the twice, okay? So if you do the same for this, the point lying on this line and this boundary straight line, then that is also 1 over norm of W, right? So, I mean, the margin is defined as 2 over norm of W, right? Are you guys all following this? So, I mean, for detailed formula, I mean, it's not that, I mean, important, but I mean, you have to, maybe it's not that difficult. You can calculate by yourself by following this formula, maybe, yeah. Carefully think, and if you apply that, then you can find that this is meaning the distance between the point here and the straight line here, right? And this is the twice of that. Okay, so the margin is anyways this 2 over norm of W, right? Anyways, remember this, margin is 2 over W, norm of W, right? Okay. And then our now, how to say, objective is minimizing this 2 over norm of W, right? Right? Are you guys following this? 슬슬 졸리는 것 같은데요. 그러니까 마진을 최대화하는 바운더리를 잡고 싶은 거잖아요. Our objective is to find the straight line that can maximize this margin, which is 2 over norm of W. And that is actually equivalent to minimizing this inverse. Okay. Okay. So in mathematics, we can now optimize this function norm of W over 2, and we will find W and B that can minimize this function, okay? Then our W and B is decided, okay, as we stated before. Okay. Are you guys following this? Okay. But there's some constraint. By minimizing this, but at the same time, you have to meet this. And this is meaning that I's sample, if they are multiplied with this W and added with B, uh, and then multiplied with their class, class label, which is either +1 or -1, then that should be larger than or equal to 1. We already see that these red samples, their yi is +1. That's the label, right? And these white samples, their yi is -1, okay? And I already told that red samples, their wx plus b is positive, okay? So positive values multiplied with +1 will be larger than or equal to 1, okay? And here, yi is -1, and wx plus b is negative for these samples. So negative samples are multiplied with -1. Their values are larger than or equal to 1, okay? So all the samples in the 2D graph have to meet this, okay? Are you guys following this? So for n samples, which means every sample on the graph, if they are multiplied with this W and B, which is the parameter of SVM function, and then multiplied with their labels, which is either +1 or -1, then it should be larger than or equal to 1. So this is meaning, all samples have to be, correctly classified. This means all samples in the graph have to be correctly classified, and at the same time, we have to minimize the inverse of margin. Okay. Are you guys following this? Okay. So that's the thing which coincides the explanation I already provide you, right? So there are a lot of boundaries that can meet the constraint, okay? The yi multiplied with wx plus b is larger than or equal to 1, then all the samples are correctly classified, and there are multiple straight lines that can meet those constraints, but one straight line that can maximize the margin. And equivalently, we will find one straight line that can minimize the inverse of the margin. Okay. 이해 안 되는 사람 있나요? Is there anybody who is not following this? Okay. Okay. So, when making this type of objective function, you can optimize W and B that can minimize this objective function and at the same time meeting this constraint. There are already many mathematical solvers for doing this, but basically they are using some gradient, and they are mostly gradient descent algorithm. That is also useful for understanding the deep learning. Can be usable to optimize this W and B, but we will learn about that in detail in the later lectures. Anyways, you can believe now that there's some mathematical method that can obtain this W and B that meets these conditions, okay? And actually, when you find the solution, using the SVM optimizer or um, I mean other way, there's a lot of optimization algorithm for optimizing this type of objective. But the thing is, the solution, especially for this problem, there's already solution is uh, obtainable in this type of closed form. There exists this type of closed form solution for the SVM. Because this is simple case, I mean, having just two classes, I told about two class problem, and also this is the simplest form of the SVM, which is not, I mean, just finding this straight line, and also the data are linearly distributed, okay? And we will learn about nonlinear case later in this lecture, okay? Anyways, this is the easiest case, and this W is having the closed form solution, actually, okay? Instead of doing optimization, you can actually calculate the W using their I samples label and some alpha value and the xi, which is the input, okay? Input x and yi, some alpha value, which is the positive, okay? If you take this, I mean, the W is can be how to say obtained for uh, summing over all the samples in the graph. Okay, this W is actually having the closed form solutions like this. And maybe for the new sample, before that, I just want to explain this formula multiplying W to the input X and adding B scalar is equivalent to exchange this W with this solution, okay? So we can substitute this W with this closed form solution, okay? And you can now realize that this n number of samples are training samples, okay? But when new samples are coming, uh, when new samples are coming, the thing you have to do is when using this type of formula, you can actually dot product between new sample and your training samples, okay? Your eyes training sample and their relevant information, then this part is obtainable, right? And you can add some scalar to output some positive or negative value. And if that value is positive, you can classify that as a positive class, +1 class, right? And if that value is negative, then you can classify that as -1 class, okay? Are you guys following this?
I may be missing from some part, but where the alpha value comes.
I mean, this is some positive value, but I mean, yeah, this can be obtainable. I mean, during the optimization actually. So I mean, you can now omit this part. Okay, yeah. Anyways, you can now grasp roughly your SVM classifier is I mean formulated via the dot producting between your training data and your testing data, okay? So in the support vector machine, actually W, as you mentioned, W can be obtainable from the alpha value, okay? But this alpha value have to be found. Okay? So I mean this closed form solution is actually have to be performed first finding the alpha value, and this alpha value is having some complicated process to find actually. Have to be found via the optimization actually. But anyways, I just want to tell you about these things. Okay. Conceptually, the SVM can be formulated like this. Okay. And during the training of SVM, you can now can find, instead of W, you can find alpha value and B. Okay. For each sample, you have to find alpha value and B. And after finding these parameters of the support vector machine, the thing you can do is for the unknown testing value, you can do dot producting with your eyes training data. And if this output is plus, then you can classify it to +1 class. Okay. And if this value is negative, you can classify that unknown sample as the -1 class. Okay. So this is the SVM classifier. Okay. Are you guys understanding this? Okay. But the thing is, this works relatively good for the linearly separable cases. Okay. So what linearly separable cases means? So if data are distributed like this, and if you can draw just one line that can separate these two distributions, then it is called as linearly separable case. Okay. And of course, I mean, in linearly non-separable case looks like this. Okay. So you cannot draw just one line, one straight line that can divide these two categories. That is called as linearly non-separable case. Okay. But I mean, in real world, there are data, more data that lie on these nonlinear cases, right? So linearly separable case, that is kind of an ideal case, which is the easiest case. And most of data distributed like this, having complicated boundaries. Okay. So so far we learned about the linear SVM. This is formulated simply, but for dealing with such non-linearly distributed case, the nonlinear SVM is proposed. And actually, that is the algorithm that records SOTA, okay, for early, I mean, 2010s, okay. Okay. But see, the idea that can develop. So I mean, they'll propose very simple trick that can be added to this linear SVM. We call the previous SVM as linear SVM because it can deal with linearly separable case. But if you want to extend linear SVM into nonlinear cases, um, I mean, there are several works proposed to, how to say, properly deal with this nonlinear case. But the idea was quite simple. I mean, if you, to say, if you see, I mean, this is visualizing the linearly separable case, okay? Black samples and white samples, they are having two classes, and this straight line can divide these samples well, okay? But if your data looks like this, okay, then this is the example for nonlinear cases, okay? We cannot draw just one line that can divide this distribution. But the idea is we can, how to say, transform these samples if these features are lying on the one dimension. It just looks like this. If we, I mean, somehow it can be seen in this viewpoint that is non-linearly separable case, right? But if you apply X square transformation on the X data, okay? So, I mean, these X values are, let's say this is 0, having the 0. This is X0, X equal to 0 line, okay? Then if you go further from X, further from the origin, then these values are having the larger X value, and their X square value looks like this, right? And if you go further from origin in this direction, it also becomes like this, okay? When you see the original data in this transformed, transformed space, okay? Then you can now draw one straight line that can classify this white and black sample, right? I mean, this is the idea of extending your linear SVM into nonlinear cases, okay? So you will now transform your feature, which is the X vector, by applying some nonlinear transformation, okay? I mean, when doing that, we cannot guarantee it can be like this, but there becomes, there are more possibility for dividing the samples with just one straight line is happening. There could be more possibility. We cannot guarantee, but there could be more possibility, right? So again, this was required for explaining this nonlinear case. Okay, so I already explained that this SVM classifier, which is the function f, is having multiple parameters, right? But this was W, and now is parameters by this alpha, right? And this is the information from the training data, okay? And this is the testing data, and this is also another parameter, okay? This is the SVM classifier. This is only applicable to linearly separable case, okay? So somehow we want to transform the training data and also the testing data, okay, to somehow wanting to have this type of opportunity, okay, to classify non-linearly separable case, see them in different feature space, different nonlinear feature space, and see if they can be classified with a straight line, okay? So we will apply this pi function on the X to transform those features into nonlinear space, okay? And this, this formula is all the other things are similarly obtainable. All the W and P, they can be optimized similarly, and even finding margins can be samely optimizable, but only this part can be changed, okay? So we call this as some corner trick. So corner here is different from what you learn from CS department, right? So it is not the term for system, right? OS system, but this corner means some transformation matrix, maybe. Yeah, corner means that, okay? So we call this pi as the corner function, okay? Are you guys following this? Okay. So we can define multiple nonlinear functions for this pi, okay? But instead of applying pi for each samples, we always calculate the paired function like this, okay? This is easier to calculate, okay, and easier to formulate. So we always do this instead of applying pi function for individual data. We define the paired corner function, okay. The corner function, their input is always 2 vector, and we return just one value that defines the distance between these 2 vectors, okay. So this Gaussian RBF corner is one of the corner function, and there are plenty of many corner functions, okay. And they are somehow mapping the original features into nonlinear space and to give us this type of possibility, okay. Okay, so I mean, this is the nonlinear SVM, okay. The corner by using this type of corner tree, you can, I mean, you can reuse the formulation of the linear SVM, just replacing this dot producting with the corner functions, okay. And yeah, and using this nonlinear SVM, you can even classify this type of samples which lie on the nonlinear space, okay. Okay, and now I will introduce the code for indeed implementing the VOW pipeline, okay. So we will, for this exercise, we will use the Caltech 101 data, okay. So this is the one of the popularly used for image task, okay. So as I already told you, image classification, it has the images having one main object inside, okay. So if you see Caltech 101 data, so this is proposed by the Caltech and having 101 classes inside. So that is called as Caltech 101 data. And how to say, anyways, they are having images having one main object inside. So the aim for us using this data is to classify images according to their main object, okay? And we will implement that using the BOW pipeline, okay? Okay. And here, I mean, those are, how to say, uh, I mean, these are code for implementing the one I explained here, okay? So first, we have to extract the features from all the patches of the training data, okay? So we, that code, that slide is actually showing that, okay? So here, this for loop is actually the loop for extracting features from each images, okay? Um, okay, so actually, and for this feature, we will use this ORB feature extractor, which is already implemented in the OpenCV library, okay? And when doing this type of assignment, I mean, actually, this will becomes your assignment 1. So please become familiar with this, okay? And when fulfilling your assignment assignments, I'm recommending to use this type of code. And what this code is doing is they are actually connecting the Colab environment with the Google Drive. Okay. So this two line of code, I'm not sure. 뒤에 있는 사람 보이나요? 이 앞에 두 줄, 맨 위에 두 줄 보이나요? 보여요? So if you type these two line of code in your Colab, then there are some messages outcome. And if you agree everything, then your own Google Drive is connected to the Google Colab. Okay. Unless if you do that, the other way to upload data is, at the first lecture, I showed you how to upload files in the Google Colab environment, right? But if you refresh Google Colab, the files uploaded in that way are erased. Okay, so if your files are big, like few terabyte, few gigabyte, then it may take few hours to upload every data into your Colab. But if you refresh, everything is erased. So that's not efficient, right? But if you upload your data, even it is few gigabyte, you can upload that in your Google Drive, okay? And Google Drive, it holds all the data, right? And then you can connect your own Google Drive that is holding your data with your Google Colab environment, okay? So with these two line of code, okay? So if your data have to be used in your Google Colab environment is big, then I'm recommending to use this two line of code. Okay. So in subsequent assignments, you also need to upload and connect your Colab with the, you have to use big size data in the Google Colab environment. So I think this is most efficient way to use the big data in the Colab, okay? And these are the code for importing some packages, okay? NumPy and OpenCV, okay? And this is specifying the image path, okay? Where the training images are lying on, okay? So this is my path, but if you're by applying these two line of code, if you link your Google Drive with your Colab environment, then you can go to this type of path, okay? And inside this path, this means the Google Drive. So inside this path, you can freely access all the data you previously upload in your Google Drive, okay? And we will initialize our feature extractor here, okay? And the objective here is we have to read all the training data, okay? So this is the one for that. So we have to calculate the image path, training image path, okay? DIR path is the one maybe specified previously, maybe here, base path plus category, okay? So we will only use two categories for this. Originally in Caltech 101, there are 101 classes, but here in this project, we will use just the two type of classes, airplane and motorbikes. So basically our task here is to classify images into airplane or motorbike, okay? And here we will first extract the feature using this ORB descriptor from all the training data, okay? So this for loop is actually doing that, okay? And then what we have to do is we append actually in this train underbar features variable, we actually append new feature descriptor, right? The size of the features extracted from the image can be varied according to the image, because there are many local patches can be obtained for some image, and fewer local patches can be obtainable from some other images. So the total number of feature descriptors can be varied according to the images. Okay. Anyways, we will append the training features, which is extracted from the training images. And then we will apply k-means clustering algorithm, okay, as we learned, on the train features, okay. And then dictionary size, this means the number of visual words, okay. This is the k value in k-means clustering, right? And actually it determines the size of the visual words, okay. And criteria, that's the, we will use the same two criteria, maximum iteration number or the minimum varied values, right? If the clustering converges, the centroid is not moving, I mean, much. So this is the, threshold. If the centroid is not changing, with this amount of threshold, then you will stop, okay, the clustering. Okay. So you will use these two type of criteria, and you will also use the random initializing the centroid. Okay, and here, this dictionary becomes the centroid. This is holding the information for the centroid. Because we set the k value as 50, there are 50 number of centroid, okay? And that centroid is having the same dimensional feature vector. If the feature vector is, I'm not exactly remembering the dimension of feature, but that is actually 256 dimensional vector, maybe. I don't know. Yeah, it could be varied. Anyways, there are 50 number of that dimensional vector. That's the centroid, okay? And we will save that in numpy as the numpy variable, right? Because we don't want to re-execute this every time, okay? Because the k-means clustering has the randomness, okay? Because we randomly initialize the centroid. So every time we run the k-means clustering, the resultant centroid could be varied, okay? So once we learn this, before doing others, we have to save the learned centroid as the file. And subsequently, we will load the centroid from this saved file. Okay. Okay. Maybe dictionary, the feature dimension is only 32. Sorry about that. Okay. So because k is specified as 50, there are this dimensional centroid that is obtained. And this is the part for implementing, making histograms using the visual words. Okay. So for doing that, we have to have the dictionary. Okay. Dictionary, we have to use that. Okay. So, but in OpenCV, when naively implement these things, we have to calculate the our extracted features with the 1 of 50 visual words we found from the k-means. But this KNN, which is the nearest neighbor algorithm, that can make us do this type of things easily. Okay, so we will use that. So anyways, but this KNN is find the nearest visual words for the inputted extracted features. Okay, so this is actually used here. So KNN find nearest for that descriptor, which is extracted from the image. You will find the nearest code word, visual word, okay? Because this KNN already have this centroid information. So when inputted this new descriptor, you will find which visual words are the nearest, okay, to that descriptor. Okay, you can get the things using this code. So basically, this code iterates through all the training data and read the image, and extract feature and map those extracted features to one of the visual world. Okay, and then map it into the histogram. Okay, so this is the one I explained already, right? Are you guys all agree with this? Okay. Okay. And then the thing you have to do is if you make the histograms for all the images in the training data, you have to now train your SVM classifier, okay, using the histogram. Okay. And OpenCV already have SVM classifier as well, right? This makes everything very easy. Okay. So you have to make the SVM classifier, that variable here. And also you can input this train DESC. This is actually holding the histograms for all the images. Okay. And also you have to have this train underbar labels, which is indicating that image is having airplane or motorbike. Okay. Maybe either 0 or 1. Okay. Then your SVM is now classified. You're trained. The parameters of the SVM is now trained. Okay, and then you have to save that SVM. Okay, their model parameters. Okay, now the training part, the implementation for the training is over. Okay, and the thing left is you have to implement the testing part. Testing, you will read two types of images from motorbike and airplane, okay? And you will read the first image and extract features for that image and find the nearest visual words for each feature and make it as the histogram, okay? This is actually encoding finding BOW representation for first image, and this is the thing for second image, okay? And also you have to normally have to do this, apply this type of normalization, okay? So when you first get the histogram, histograms are having integer values. Each entry of histogram is having the integer values. But we normally, before applying the machine learning algorithm, we normally make their norm to have 1. Okay, so this is for doing that. Okay, if you do not apply this type of normalization, their samples distribution in their histogram space is quite far. But if you apply normalization and by making their scales to their error norm as 1, then they become to have become to be in some small how to say space, and this is easier for machine learning algorithm to find the boundaries. Okay, so this is quite simple things, but so you may can omit this, but in practice, applying normalization is quite quite important for machine learning algorithms. So don't forget about this. And then this SVM.predict will perform the testing on the new extracted samples, and this result will give us the class inferred for that testing images. Okay, are you guys following this? And yeah, so if you try to see this result outputted from this SVM, then it is meaning 0 or 1, and meaning the 0 is, I mean, how to say, meaning the airplane, and 1 is meaning the motorbike. Okay, so, and if you visualize image 1 and image 2, you indeed see those input images are like this, and their inferred labels are 0 and 1. Okay, so this BOW pipeline indeed working now. So, I mean, the implementation here might be assignment 1. So maybe you can just type and practice. Okay. Okay. So the remaining thing is very short, but I will continue this maybe next Monday. And after this, we will maybe learn about the basics of the PyTorch and gradually moving towards the deep learning, how to implement deep learning. Okay. Okay, thank you. See you next Monday.